Hello, and welcome to a lecture on design procedure for axisymmetric paraboloidal reflectors. I'm Steve Ellingson. Here's an overview of this lecture. First, I'll present a baseline reflector design. The purpose of a baseline is to have a known good design from which one can iterate to find the design that satisfies the specific requirements. Then, feed synthesis. I'll talk about how to go about selecting the Q in a cosine raised to the Q feed model. And this is possible given the edge illumination and the F over D. Then the design procedure. And I'll follow that up with a very simple example to demonstrate how the procedure works. Then I'll discuss feed modeling. In other words, how to find Q that we need in the design procedure from pattern data. So when I talk about the design procedure here, I'll just assume cosine Q. But of course, you can't necessarily buy a cosine Q feed. You get practical feeds. So I'll talk about the problem of how to get Q to use in the model from pattern data. And then the path forward. We'll find there's a couple things that we probably need to explore in more detail to do a proper job of reflector design. So here's the baseline reflector design. What we do is assume a design which is already known to have reasonable performance. So we'll restrict our focus to circular axisymmetric paraboloids. In that case, we know Q equals 2 is a reasonable value. And we know from this that edge illumination approximately equal to minus 11 dB optimizes illumination efficiency. And this is a very broad maximum. In other words, minus 10 dB is probably okay. Minus 12 dB is probably also okay. The idea is to have a value that you can start from and then iterate to get to the design that you seek. Now, under these conditions, we know that the gain, that's G, is equal to the optimum directivity, right? And the optimum directivity is the directivity corresponding to an aperture which is uniformly illuminated. So we found in a previous lecture that for the baseline design, we should expect an aperture efficiency of 82%. So here it is right here. And then the optimum directivity, the directivity of a uniformly illuminated aperture, is just pi times diameter divided by wavelength quantity squared. Now this D is diameter. One of the great difficulties in reflector design is that we use G and D for multiple purposes, so sometimes it gets confusing. So just be clear, D here is diameter, D sub U is a directivity. Also, we know from previous work that the half-power beam width of this baseline design is about 1.18 wavelength divided by diameter. And that, of course, has units of radians. Now, how did I know this? You may look back at the lecture notes and say, no, I don't think we actually worked this out. But we did it before we started talking about reflectors. What I did is discussed in general how aperture tapers worked and how they modified the characteristics of the half-power beam width and the side lobe level and so on. And in fact, this is from your textbook, Table 9-2, also appears in the lecture notes. The idea here is that we have a tapered illumination, maximum in the center, goes to some non-zero value called C here at the edges. Now, C is just edge illumination. And furthermore, we can make the argument that n equals 2 corresponds to the Q parameter in a cosine squared feed pattern. So if we take edge illumination to be 11 dB, then we should be right in here between these two rows of this table, which you can see 1.18 times lambda divided by D, 2A is D, is right here. And in fact, you could estimate the side lobe level from this, And you could also estimate the taper efficiency from this. So these tables are somewhat useful for getting a design started. Okay, feed synthesis. We know that in general, we have the edge illumination is 1 plus cosine theta naught. Remember, that's angle to the rim. Divided by 2 times the normalized feed pattern evaluated at the angle to the rim. And for a cosine Q feed model, we have this. Just the same leading trigonometric factor, and then cosine raised to the Q power evaluated at theta naught. Now we can solve this for Q. Solving this expression for Q, we get this rather ugly looking expression, but not difficult to use. It's the ratio of logarithms. In the numerator, we have edge illumination, and we have f over d. In the denominator, we have f over d. So given f over d and edge illumination, we can solve for the value of q that fits the cosine q feed model and gives us that edge illumination. Okay, so here's the design procedure. The input first. This is the given. A specification for gain, G, at some frequency. Perhaps also constraints on half-power beam width, on side lobe level, on cross pole, and so on. But these are secondary, at least to get the procedure started. Choose edge illumination to be minus 11 dB to start, for reasons we've discussed already. Then, get the starting value of the diameter. Remember, this is diameter, using the expression that we found in the previous slide. Then choose f over d. Now we've chosen d, the diameter, so it's simply choosing for f over d and choosing focal length are the same thing. I would start with f over d equals 0.5 if you have no other basis for starting. Remember, reasonable values of focal length go something like 1/4 to 1/2. So 1/2 is on the high side, but that yields pretty good cross pole. We saw that in a previous lecture. The downside is it's relatively large focal length. You might find that the f required to give you f over d equals 0.5 is too large, in which case you'd scale this back a little bit to start. If you can accept the value of f that's required to give you f over d equals 0.5, then you might as well proceed because you know this will give you a good cross pole. Now, with those two things specified, f over d and edge illumination, then Q is constrained. We just saw that in the previous slide. Given these two things, you solve for Q, and now you've got the feed, because the feed is described by Q. So now you can calculate the pattern. That is, you can get the gain, you can get the half-power beam width, you can get the side lobe levels, you can get the cross pole, all the things that you might also be concerned about. You can do this using geometrical optics aperture integration, or you can do this using physical optics surface integration. And we talked about both those in a previous lecture. If you're in a hurry and you're concerned only about the gain, then you could use one of the simplified or approximate directivity computation methods, where you only integrate once over an aperture. See, if you calculate the pattern and then calculate directivity by computing solid angle from the pattern data, that's a lot of integration. You have to integrate once for every pattern point, and then you have to integrate again over the pattern to get beam solid angle. Whereas if you're interested only in the gain, you might as well use the simplified approach and integrate just once over the aperture. That'll be a lot faster. Now, if you're unhappy with the design you end up with, or how these things turned out, then you decrease the focal length, because that's the parameter that remains free in this procedure, and repeat. And then you would iterate until you found an acceptable trade-off among these parameters, parameterized now in the focal length. And the output then is the diameter, the f over d, or alternatively just the focal length, and q, which describes the feed. Now I want to make one other point here. Like all complex design procedures, the design really consists of two phases. One is synthesis, where we start off with some initial specs and we come up with other things that describe the design. Here, F over D in edge illumination, and Q. Then, in analysis, you take whatever design you came up with in the synthesis phase and you analyze it. Right? And then typically there is some iteration here. So you're unhappy with the result from the analysis, you change the design, you repeat the synthesis, you analyze again, and so on. So like most complex design problems, there can be some, and typically a lot, of iteration between these two things. Okay, an example. This is a modified version of a problem from your book. It's example 9-9 in the 2013 version of your textbook. Given a 10 gigahertz reflector system, we'll just consider that one frequency, 10 gigahertz, prime fed, axisymmetric, circular, it doesn't say that here, but that's implied. And we require the gain to be at least this, at least 45.6 dB. Now, this is a modified version of the problem in the book. In the book, your authors specify half-power beam width should be a certain value. I kind of find that to be a little bit strange. Most reflectors are not designed to have a certain half-power beam width. Sometimes they are, but usually there's a gain spec as opposed to a half-power beam width spec. So this is the same example. I've just changed the requirement, and we'll end up with the same design. In any event, we're going to try to get the gain above 45.6. And of course, there's always a constraint. In this case, we want to minimize diameter. And again, that's a very common thing. You need to achieve a certain amount of gain, but you don't want to make the reflector any bigger than it has to be. And then also we have these secondary considerations, side lobe levels, polarization properties, and so on. So the synthesis phase goes like this. Here's our expression for gain for the baseline design. That implies that the diameter should be 2 meters. We simply solve this expression and we get 2 meters for the diameter. Using edge illumination of minus 11 dB, because we know that gives us optimum illumination efficiency for the baseline reflector design. And F over D equals 0.5 because we don't have a more specific idea of where to start. We get Q equals 2. The analysis, very simple. You can do it by GOAI. You can do it by POSI. You get the pattern. You can get the gain. You can get the half-power beam width, the side lobe polarization, and so on. And those things are shown in your book, so I'm not going to repeat them here. Now, if you weren't happy with what you got here, then you would simply reduce F from 0.5 or change Q. Maybe there's some constraint on the feed that wasn't addressed in the initial list of requirements. And then you simply repeat these steps. So analysis to synthesis, synthesis back to analysis, and so on until you get a design that you like. So here's some comments on this procedure. First, as I've said now several times, iteration is required. You need iterations to find the acceptable joint values of the diameter, the F over D, and the feed. Also, practical feeds are not exactly cosine Q feeds, so you typically need more iterations once you get a value of Q, and these additional iterations take into account other feed choices. And this brings into play the whole issue of feed modeling. Then you need additional further iterations to design the feed mount, something we've said almost nothing about, but that feed doesn't just hang in air. It has to be attached to the reflector somehow, and the way you attach it to the reflector could affect the performance. And then the feed itself contributes some blockage. Now, we saw in a previous lecture that this blockage doesn't necessarily have to be a factor, but it could be. So these are other iterations, once you get these things straightened out, that you may need to apply. And you may find that something here turns up that requires a change in this design. Let me repeat some things that you should already know at this point, but just to make them explicit, because they come in useful to keep in mind during the procedure. One is that decreasing F over D reduces F, which makes the system more compact, and increases cross-pol. All right, so there's one trade-off that you have to keep in mind. Also useful to know is that increasing edge illumination, which is the same as reducing Q, increases gain, which seems like a good thing, but also increases side lobe level. And that's because when you increase the edge illumination, the edges are more brightly illuminated, and the edges are what create the side lobes. So increasing edge illumination increases side lobe level. So these are two sets of trade-offs that you should keep in mind in order to approach this iterative procedure in the most efficient way, so you don't do iterations that don't accomplish the goals that you're seeking. Okay, feed modeling, getting Q from pattern data. The definition of a cosine Q feed is this: normalized feed pattern varies only with theta sub f, and that pattern is cosine raised to Q power of theta sub f. We can solve for Q. We get log of the normalized pattern divided by log of cosine theta f. Now, if you're shopping data sheets, for example, if you're looking through a catalog of feeds, typically they won't tell you what the effective Q of the feed is, even though that would be useful to you as part of this design procedure. But you can calculate one, and the way you do it is you take advantage of this equation. You take a value of theta f, which we'll call theta sub f test, and that value is typically whatever angle it takes to be at either the 3 dB point or the 10 dB points. It's your choice because this is an approximate thing to start off with, but you make some choice here about what you want to call or how you want to define the test angle. And once you do that, you can read off the pattern value from the data sheets, because this will now be something that appears in the data sheets, and then you can calculate Q from that. So this is a way that you can get a value of Q from pattern data in data sheets and other sources. Now, this doesn't account for polarization, and note that some feeds have very poor polarization properties. So this might be useful to get you started or to get something a little bit closer to the final design, but at some point you're eventually going to have to face this issue. Okay, now using pattern data. To account for a candidate feed as part of the design procedure, you need a volumetric analytic expression for the feed pattern. Now we're talking about the analysis phase here, right? In this previous slide, we were talking about the synthesis phase. This is talking about analysis feed modeling. Now, you might be able to obtain pattern data. Perhaps the vendor provides it, or perhaps your organization can make these measurements. Typically what happens, however, is that you don't get the volumetric data, in other words, the pattern data for all values of theta f and phi f. Rather, you just get it for the E plane and the H plane. That is just two values of phi sub f. Now, we'll come back to this issue in a later lecture of how to take just these two pattern cuts and convert them into a volumetric expression, at least a way to do that approximately. I just want to say here that it's possible to do that. And again, you may or may not need to account for polarization in the reflector system design process. So, the path forward. It has emerged that feed models are important. We need to know better how to accurately represent feeds to do a good job with design. We can see that now. And we also need to know better about how actual feeds work. Now, it should be no secret at this point that most reflector antenna systems are fed by a horn antenna. So we're going to have to take a look at how horns work. Also, I've completely bypassed the issue of the far side lobes. Remember, when we have a reflector antenna system, there's a reflector, there's a feed, we get a main lobe, we get the first few side lobes, and those are things that the method of geometrical optics aperture integration or physical optic surface integration do a good job with. But what about the pattern back here? Or what about side lobes going off in these directions? These things will couple the antenna into its surroundings. So if you have the ground, if you have a mounting structure, or if you have other antennas nearby, these side lobes will couple this antenna into adjacent antennas. And you may need to know about that. So to do that better job with that, we're going to need diffraction theory. And specifically in this course, we'll talk about GTD. Although there are other ways. GTD turns out to be a natural extension of geometrical optics that addresses this issue fairly well. Another thing we're going to have to address is more advanced systems of reflector antennas using subreflectors. Now, subreflectors turn up oftentimes when you have a focal length which is longer than what you can accept, and you need to make the reflector more compact without reducing the F over D. And a way to do that is using a subreflector. There are other reasons to use subreflectors, but that's a big one. Now, to do subreflectors, we're going to need various combinations of physical optics, geometrical optics, and GTD. So another application of GTD will be to deal with this case where we have, say, subreflectors, and we have systems that do things like this, where the horn might be down here now. This concludes this lecture on design procedure for axisymmetric paraboloidal reflectors.